Ian Stewart, GMAT math expert, tutor and writer, and this video is part of a series of videos I'm doing featuring high-level questions that I've designed. This video is really not meant for everyone. It's meant for test takers who have already studied the topic and who are scoring at a Q40 level or above. So if that's not you, then just bookmark this page and come back when it is. My questions, they're not modeled after published official questions. Instead, they're much more like what you'll see on test day, questions testing the same familiar GMAT concepts, but in unusual or inventive ways. And the questions are quite challenging, so don't be concerned if you find some of them difficult. To get the most out of this video, you should try each question. I'll put each on the screen for 5 seconds, so press pause. But if you get stuck, don't spend more than about 90 seconds on any one problem. Let's call the first term of the sequence A. The rule in the question tells us to find the next term in the sequence. We just multiply the previous term by 1.5 or by 3 over 2. And so going from the first term to the seventh, the last term in the sequence, we'll multiply by 3 over 2 6 times. So by 3 to the 6 over 2 to the 6. We also know this last term is an integer, and if it's an integer, that 2 to the 6 and the denominator needs to cancel somehow. It doesn't cancel with 3 to the 6, so it must cancel with a, the first term of the sequence. So the first term of the sequence needs to be divisible by 2 to the 6, 64. And so its smallest possible value is 2 to the 6. And since we want the smallest value of the fifth term, we should choose the smallest value of the first term. So assuming the first term is 2 to the 6, then the fifth term will multiply by 3 over 2 4 times to get to the fifth term. So the fifth term will be 2 to the 6 times 3 to the 4 over 2 to the 4. And cancelling the 2 to the 4, 3 to the 4 times 2 squared, 81 times 4, 324. So this question perhaps illustrates the limitations of number picking. A lot of people, I think their first impulse in seeing a question like this would be to plug in various values of x. But if you wanted to see that item 1 here is not always true, you'd need to plug in a value of x at least equal to 7, and that's not an easy number to work with here. It's much easier to see that 1 can be false just by doing the algebra. And if we rewrite this inequality, we're just discovering which values of x would make this inequality true. And we can rewrite 4 to the x plus 1 just as 4 times 4 to the x, and then divide both sides by 4 to the x. It's a positive number, so we don't need to flip the inequality. And then we get 4 is greater than 5 to the x over 4 to the x. So 4 is greater than 5 over 4 all to the power x. 4 is greater than 1.25 to the x. And 1.25 to the x, certainly it's less than 4 sometimes if x is a small positive integer, but if x is large enough, 1.25 to the x could be as big as we want it to be. So item 1 is certainly not always true. For item 2 here, number picking might actually be the fastest way to see that 2 doesn't need to be true, because for most values of x it's not true. If you just plug in x equals 4, for example, you'd get 5 to the 4, 625 on the left side, and 4 to the 5, 2 to the 10, that's 1024 on the right side. So the inequality is not true even when x is that small, but we could do this algebraically as well, just divide both sides by x to the 4. And then taking the exponent to the outside on the left side, we have this fraction x plus 1 over x all to the power 4 on the left, which is just 1 plus 1 over x to the power 4. And that's very close to 1. If x is a large number, that's definitely not going to be bigger than the x on the right side if x is large. So item 2 is certainly not even usually true, let alone always true. And lastly, item 3, if we just imagine x is fairly large, if you take a 4th root, that's going to be bigger than the 5th root if you're taking roots of the same number. And here we're taking the 4th root of a larger number, x plus 1. that's definitely going to be bigger than the fifth root of just x. So item 3 should always be true. Kind of more formally, the fourth root of x plus 1 is always bigger than the fourth root of x if, x is a positive integer. And the fourth root of x is always bigger than the fifth root of x, except in the one case where x is 1, I guess. And so the fourth root of x plus 1 is definitely bigger than the fifth root of x if x is a positive integer. And item 3 must be true. So here we have a kind of quadratic inequality question. If we look just at statement 1, if we rewrite it with 0 on one side, x squared minus 8x plus 16 is greater than 0, and that's one of those standard x minus y squared kind of patterns. If we factor it's x minus 4 all squared is greater than 0, and that's almost always true. Squares are almost always positive. Really, this just tells us x is not equal to 4. The only situation when a square is not positive is when it's exactly equal to 0. So statement 1 tells us almost nothing, and the answer is almost certainly going to be B or E. Statement 2 is the harder of the two statements. Here we have a variation on a quadratic inequality. I guess technically we have a cubic inequality here, and there's quite a few ways to analyze an inequality like this, but the most flexible is to factor. So if we first get 0 on one side, notice we can take an x out right away, leaving us with x squared minus 3x minus 4 in the brackets. And to factor that, we just want two numbers that multiply to minus 4 and add to minus 3, so those numbers are minus 4 and plus 1. So we have our three factors, and we can now write them in increasing order. X minus 4 is always less than x, which is always less than x plus 1. And we know when we multiply those three factors together, the result needs to be positive. And there are two ways that could happen. It could be that all three factors are positive. And as long as we make the smallest factor positive, that will guarantee that the other factors are positive as well. So all three factors will be positive provided x minus 4 is positive, or in other words, provided x is greater than 4. So that's one way this inequality can be true, but there's a second possibility we also have to consider. It might be that two factors are negative and one factor is positive. And if two factors are negative and one's positive, well, the largest factor would need to be the positive factor. So in other words, x plus 1 would need to be positive, or x would need to be greater than minus 1. And for the two smaller factors to be negative, as long as the larger of those is negative, then the smaller factor will certainly be negative as well. So as long as x is less than 0, we can be certain the two smaller factors are both negative. So we have two negative factors, one positive factor, provided x is somewhere in between 0 and minus 1. And so statement 2 doesn't ensure that x is greater than 4. Statement 1 wasn't very helpful, so the answer is E. If you enjoyed these questions, I've written 4 long problem sets full of high-level questions like these, along with a set of books covering all of GMAT math that teach my conceptual approach to the test, which is perfect for high-level test takers. And if you're interested in any of that material, you can just visit my website. The link is in the description below.